Boundary layer. So this is the region that is adjacent to a surface over which the velocity changes from free stream to zero. Boundary layer may be something that you've heard relative to weather. And this occurs because of the fluid's viscosity. So let's say we have this black, thin, flat plate moving through a fluid. And the fluid is represented in blue. And this nice flat portion at the top and bottom here, that's the laminar fluid flow. Now the boundary layer is this bottom part here. And then behind this laminar boundary layer, we're going to be kicking up dust for our turbulent boundary layer. These little dotted lines here, this is the shear that is created as that plate moves through the moving fluid and creates these boundary layers. So some important information here. First, this plate has two boundary layers, one on top and one on bottom, because it's moving through the fluid and has two sides to the plate. If we're talking about weather and we're talking about Earth, the wind on the surface of the Earth is just one boundary layer. So next we have delta. Delta represents the thickness of the boundary layer up from the surface of the object moving through the fluid to 99% of that free stream velocity. So that's going to be, somewhere here-ish. The critical point is where the turbulence begins. So again, coming back up to our picture, that's going to be here. The transition point is where the boundary layer is fully turbulent. So on my little picture here, that's going to be over here. We've got all the little swirlies for our turbulent boundary layer. The laminar section is small and does not contribute much to drag, but the turbulent section certainly does. Because of all these little squiggly eddies here, viscosity is increased, as is shear stress. We have two types of boundary layer flow that we can talk about here. The first is Couillette flow, and that's where we've got, in this case, a stationary plate at the bottom, but we'll put a moving plate up here. And that makes the boundary layer look something like this. The other one is the Hillshaw. Where both of the plates are stationary. So when the flow is going between these plates, it's parabolic. These shapes are just like the boundary layers that we had earlier that are created by friction and drag. One way to represent all this internal forces, viscous forces, surface to fluid interaction is the Reynolds number. We introduced Reynolds number when we were talking about similitude and dimensional analysis, so let's get a little bit deeper. If we're talking about circular pipes, we're going to have the characteristic length of the pipe, which in this case would be the diameter, and then we're going to have this average velocity going through the pipe. So we have our Reynolds number, which is going to be the material properties of the fluid, so that's going to be the density and the viscosity, and then in this case the average velocity and the diameter of the pipe. We can also rewrite Reynolds number to be 4 times Q over pi d nu, which is the kinematic viscosity, and all we've done here is replaced velocity with Q over A. A very large Reynolds number means that the inertia is large. That it is turbulent, which means that friction cannot prevent random fluctuations, okay? It's going to take a lot for there to be a big fluctuation. And depending on what text you're reading, that's going to be greater than 3,000 or 4,000 for a Reynolds number. On the other hand, if we have a small Reynolds number, that's going to be laminar flow. And we like laminar flow because all the little viscous forces are keeping that fluid in line, straight lines, and not the swirls. That's going to be a Reynolds number of less than 2,000. So the next question is, well, what happens if it's between 2 and 3,000? Well, that's going to be a transitional flow, and that's where things get real hairy. We're not going to deal with that much in this course. In Reynolds number, we have that capital D, or hydraulic diameter. This is the characteristic length of pipes or ducts. So if I have here a pipe cross section, and this pipe is running full of fluid, okay, this right here is going to be the cross-sectional area of the fluid, and then around this area, I'm going to draw in purple here, this is going to be the wetted perimeter. So this leads us to the equation for the hydraulic diameter is equal to 4 times the cross-sectional area divided by the wetted perimeter. For pipes and tubes with a circular cross-section, the hydraulic diameter is the diameter of the pipe or tube. But if we're talking about non-circular cross-sections or ducts, then we can have square where our hydraulic diameter is going to equal to the dimension of the square cross-section, or we can have rectangular where the hydraulic diameter is equal to 2AB over A plus B. So we've got flow that is laminar, flow that is turbulent, something in between, and these things are happening in one place when we enter a pipe. So we have a different dimension that we're entering, or we're going from a tank to a pipe. So we've got our lovely laminar flow here that's coming into the pipe. So as it is transitioning, we've got our hydraulic entrance region, and then it becomes fully developed. And that's when we reach this average velocity here in our boundary layer flow within the pipe. Okay, this entrance length, the hydraulic entrance region, LE, is going to be approximately 0.05, the Reynolds number, times the hydraulic diameter for laminar, and quite a bit larger than that. It's about 50 times the hydraulic diameter for turbulent. If the pipe is long enough, we can assume that it's fully developed and we can run with that flow. We are given this system where we have a bent pipe that is 100 millimeters in diameter and oil is flowing through it. And we want to determine if it is laminar or turbulent. And 2 is open to the atmosphere, 1 is connected to the rest of the system. We measure the pressure at point 1 to be 34.25 kilopascals. Our solution is going to be using Reynolds number to determine if it is laminar or turbulent. So I have rho VD over mu. Now I was given the specific gravity of the oil and I was given the viscosity of the oil, so this is taken care of. I was also given the diameter of the system. So what I need to find is the velocity. We're going to use Bernoulli's equation to find the velocity. So we have pressure 1 over gamma plus elevation 1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G, and we're going to neglect our losses due to friction. I'm going to set up my datum here at the bottom of 1, so that means that Z for 1 is going to be 0. It is open to the atmosphere, so pressure 2 is going to be 0. We have a constant diameter for the entire system, so that means velocity 1 is equal to velocity 2. So cleaning this up for velocity, we have our pressure 34.25 kilopascals divided by the specific weight, so that's going to be 0.87 times 9810 Newton per meter cubed minus 4 meter height, multiply this whole mess by 2 times gravity. And then we need to take the square root. And we find the velocity through our system is 0.506 meters per second. Pretty slow velocity. I'm going to guess this is laminar. But let's do the Reynolds number and check it out. Our Reynolds number is going to be the density, 1,000 kilograms per meters cubed times 0.87. So there's density times velocity that we just calculated. Times the diameter of my pipe. I'm going to convert that to meters, so 100 millimeters is 1 meter. All divided by the viscosity that we were given, or we looked up in Appendix A. And let's see, we are in kilograms, meters. All right. Our Reynolds number calculates to be 1,223, which is less than 2,000. So we are going to say this is laminar flow. What if this time we're given a 10-foot tall vertical standpipe with a diameter of 3 inches? We want to find the allowable velocity so that the water flow through that standpipe remains laminar. Remember that laminar Reynolds number is 2,000 maximum. So that's what we'll design for. So we have 2,000 is equal to density of water. We're going to assume it's standard temperature and pressure. So that's 1.94 slugs per foot cubed times velocity. That's what we're solving for. Diameter is 3 inches. So I'm going to divide that by 12 inches per foot and throw my conversion in the equation. Divided by the viscosity of water, which we looked up in Appendix A at 20.5 times 10 to the negative 6 pound second per foot squared. Solving for velocity, I need it to be equal to or less than 0.0845 feet per second.